Hello class, welcome to this video on Chapter 2 AP Statistics Practice Test. So this is part 2 of the Unit 1 review. So let's go ahead and get started. So Chapter 2 is on, probability density functions, normal distributions, percentiles, things like that. All right, so many professional schools require applicants to take a standardized test. Suppose that 1,000 students take such a test. Several weeks after the test, Pete receives his score report. He got a 63, which placed him at the 73rd percentile. So what does this mean? So it says this means that, 73rd percentile, that means that 73% of people scored below him, or scored a 63 or lower. So that's what it's saying. So Pete's score was below the median. So that's incorrect. Pete's score was above the median because remember the median is the 50th percentile, and he's at the 73rd percentile. Pete did worse than about 63% of test takers. Nope, that's not the interpretation. He did worse. He did worse than 100 minus 73, or 27% of test takers. So So 27% of test takers had his score or higher. Says Pete did worse than about 73%. No, he did better. Pete did the same as or better than about 63% of test takers. No, he did the same as or better than about 73% of test takers. So that is the correct interpretation. Okay, so for the normal distribution shown, the standard deviation is closest to what number? Okay, so for this type of problem, look to see where the tail behavior is located. We know that the mean is in the center, so we know that the mean is approximately 2, right? And so if I look at the tail behavior, it looks like the tail begins to approach or touch the x-axis. It doesn't actually touch the x-axis, but you can see that it starts really approaching it right around this mark, which is around the 11 mark. Okay, so and by the time it touches that, or it begins to really get close to that x-axis, that's about the point where you're at 3 standard deviations away. Meaning that you have almost 100% of the curve, but not quite, right? You have 99.7% of the curve, according to the empirical rule, right? So that is a good indicator of having most of the curve, and therefore that's 3 standard deviations away, which means that, okay, so 11 minus 2 is 9, right? And if 11 is 3 standard deviations away, that means we're going to take the 9 and we're going to divide it by 3. And that's going to give us 3. So that indicates that our sigma is about 3. So that if I go 1 standard deviation away, that's, so if I do plus sigma there, I'm at about 5, right? If I do another plus sigma, which is another plus 3, then I'm at about 8, and then another plus sigma, then I'm at 11. So that's 3 standard deviations away. So it's approximately going to be 3. So the answer is D. All right, number 3, rainwater was collected in water containers at 30 different sites near an industrial complex, and the amount of acidity or pH levels was measured. The mean and standard deviation of the values are 4.60 and 1.10 respectively. When the pH meter was recalibrated back at the laboratory, it was found to be an error. The error can be corrected by adding 0.1 pH unit to all the values and then multiplying the result by 1.2. Okay, so it says, multiply the result by 1.2, and then what are the mean and standard deviation of the corrected pH measurements? Okay, so this is a transformations question. Remember, when you take data and you take a set of data and you multiply each of the numbers by, say, or you add each, so let's say you have a bunch of pH levels, right? You have pH 1, you have pH 2, ... You have a bunch of pH levels. And here it says you're adding +1 or plus 0.1 pH to each of these, right? You're doing it to every single number. What is that going to do to the average? Well, that's going to shift the average by plus 0.1, right? So the average is going to be 0.1 higher than it normally is. So you got to understand that if I add the same number to each data point, the mean is going to be shifted by the same amount. You also got to understand that if I multiply a number, each of the data points by a number, that's also going to multiply the mean by that result, okay? So here we're adding 0.1 and then multiplying by 1.2. So I'm doing this and I'm multiplying that result by 1.2. So that's what I'm doing for each of these. That's going to affect the mean just as equally. Okay, so then the mean, the new mean, right, is going to be the old mean, right, the old mean plus 0.1 and then times 1.2. That's how the transformation works, right? So that's how you get the new mean. Now, as far as the standard deviation is concerned, standard deviation is a measure of spread. So you have to understand that when I'm doing a transformation on a set of data and I'm adding the same number, in this case 0.1, to each of the pHs, to each of the data points, that is not going to affect the spread. The spread is still going to remain the same. So the standard deviation does not change, okay? If I multiply by the same number or divide by the same number to each of the data points, that will affect the standard deviation. That will affect the spread, okay? So in this case, for the standard deviation, the new standard deviation is going to be the old standard deviation, not plus 0.1, because the 0.1 doesn't actually affect the standard deviation. Addition and subtraction do not affect spread, right? However, multiplication does. So we could take this and we can multiply by 1.2, and that will be your new standard deviation, okay? So bottom line is, if the old mean is 4.60, then we're gonna take that plus 0.1 or 0.10, same thing, and then times it by 1.2. That's going to be our new mean. So here in that case, we get 4.7 times 1.2. So let's see what that is. I'm going to do that on the calculator, make our life a little easier. So we have 4.7 times 1.2. So that's 5.64. So our new average pH is going to be 5.64. And then our standard deviation, it says the old standard deviation was 1.10. So we're going to do 1.10 times the 1.2. All right, so you got 1.10 times 1.2. So you have 1.32. All right, so those are your new mean and new standard deviation values. So we got 5.64, 1.32. So the answer is, it's got to be B. All right, so hopefully that made sense. You just have to, basically at the end of the day, you just have to understand what transformations do, right, to the overall. Like what happens to the, what affects, what has effects in the transformation, right? All right, so the figure here shows a cumulative relative frequency graph, also known as an ogive, of the number of ounces of alcohol consumed per week in a sample of 150 adults who reported drinking alcohol occasionally. About what percent of these adults consume between 4 and 8 ounces per week? Okay, so between 4 and 8 ounces. Okay, so between 4 and 8 ounces. So here we got 4 ounces here, which is about 20%, right? And we got 8 ounces here, which is about 60%. And that, remember, the 60% is the 60% is from 0 all the way to there, right? And then 20% is from 0 all the way to there. Well, then that means that the area in between, or the percentage in between, has to be 60 minus 20, right? That are consuming between 4 and 8. So 60 minus 20 is equal to 40%. Remember, you got to understand that a cumulative relative frequency graph. Cumulative means that you're adding it from the left to the right. So you're starting at 0 and you're adding as you go. So you're basically adding everything to the left of whatever value you're looking at. Okay, so that's what it means when they're talking about cumulative. All right, so the answer is B. All right, so 2.5, the average yearly snowfall in Chillyville is approximately normally distributed with a mean of 55 inches. If the snowfall in Chillyville exceeds 60 inches in 15% of the years, what is the standard deviation? Okay, so we're going to solve for standard deviation. It says it's normally distributed, which means we can use the z-score formula, right? It says here that the mean is 55. Okay, so we basically got something that where you have the mean is 55. We don't know what a standard deviation is, right? So we don't know what the spread is, but we do know that it says if the snowfall exceeds 60 inches in 15% of the years. Okay, so that means let's say 60 is here, right? Let's say that's 60 inches and 15%. So exceeds meaning that it's greater than, right? It's greater than 60. And they're saying that this is 15% or 0.15. So if that's 0.15 or 0.1500, then we're going to look this up on the z table to figure out, okay, well, what z-score does that correspond to? Okay, so that's what we're going to do. Okay, so what we're going to do now is we're going to find out what 0.1500 is on the z distribution. So basically what we're going to do is we're going to convert this into a standard normal distribution where this is 0 and this represents the z-axis now. Instead of the x value, which is the snowfall, we're going to do z, which is the standardized score. So that means it's going to go by ones, right? The standard deviation. So this is going to be my 15% over here. Okay, and we're going to see what that z-score is right here. So z equals question mark. So we're going to find that out. So we need to, in order to do that, we need to look up an area to the left. So we need to figure out the area to the left. Well, if this is 15%, then this here is 1 minus that, right? Which is 85%. So 8500. So the reason we got to look up to the left is because we're going to use table A for this. Okay, so here is table A. This is the standard normal distribution table. It always gives you the area to the left, right? And therefore that has to represent 85%. So let's go to see that. So we're looking at this situation where this is 15% and this is 85%, right? So we're looking up the area. So 85%. This seems to be the closest one, or pretty close to it. Actually, this is the closest, right? 8485 is closer to 85% than 850. Actually, no, 8508 looks pretty darn close. Yeah, so this is actually the closest to that. All right, so then if that's my area, my z-score that corresponds to that, this is z, right? This is z here and z there. Z to the left and z bottom. So we got a z-score of 1.0, 1.04. That's approximately my z-score is 1.04. Okay, so now we know what the z-score is. So let's go back to our problem. So we've established now that the z-score is 1.04 approximately. And that makes sense according to my graph. It's a little bit above the 1. So now we're going to use this to find the standard deviation, because now we know that the formula for the z-score is x minus mean, x minus mu divided by the standard deviation, right? Well, then that's true. Then z is 1.04. So we know what that is now. And we know that x is the 60 inches of snowfall. That was my x value. Mean is, that's the mu, is 55. And we don't know sigma, right? So we got to find sigma. All right, so before I continue solving for sigma, I'm going to show you how to find the z-score using the calculator, okay? So I'm going to show you that now. So here is the calculator. We're going to show you how to do that result. Again, when you do the calculator, you have to use 0.8500. You can't use 0.15 or it's going to give you the incorrect result. So just keep that in mind. You still got to subtract from 1 and do this green part, okay? All right, so first thing you're going to do is second vars. So second vars. And then var stands for variables, so you're trying to do a bunch of variable stuff. So now you're going to go to inverse norm. The inverse norm function is it gives you your x value or your z-score, whereas this gives you your area right under the curve. So inverse norm, so you enter, and now the area provided, we want to provide 0.8500 or 8, we could just put 85. And then the mu is 0, the sigma is 1. That means we leave it as mu 0, sigma 1, because we want to know what the z-score is, and that means that we want the mu to be 0 and the sigma to be 1 there, okay? And we also don't know what the sigma is for this guy anyways, so there's no point. So let's do this. There you go. So our z-score is about 1.04. You can see that from there. So it's approximately. All right, so that takes care of that. So anyway, so now let's go ahead and solve. Now that we know it's 1.04, so we're going to solve for sigma. So multiply by sigma on both sides. So you get 1.04 sigma equals 60 minus 55 is 5. Then divide by 1.04 to get your sigma. So we get 5 divided by 1.04. Okay, so about 4. Yeah, it looks like about 4.8. 4.8 or 4.81. Okay, and then we'll see which the one that matches up with. So 4.81. They got about 4.83, so yeah, that seems to be the closest. So it's got to be A. All right, so hopefully that made sense. That one was pretty involved, and it's actually a really good question. A really good question to kind of for working on your normal distribution skills. All right, so the figure shown is the density curve of a distribution. 7 values are marked on the density curve. Which of the following statements is true? So this is the density function, and it looks to be skewed left, right? So the way that it looks here. Okay, so remember that a density curve, the area of a density curve from negative infinity to infinity, or from for the entire curve, basically from left to right, is got to be 1. All right, so it says the mean of the distribution is E. It says which of the following statements must be true. So when we answer this, the mean of the distribution is E. Well, is this the 50% mark? Right? It does not seem like it's for the 50% mark, because this area right here is smaller than this area right here, right? So E cannot be the 50% mark, or the median. I'm sorry. They're talking about the mean. Okay, so let's look at approximately where the center is. So let's just assume that maybe this area around here is like the median, right? Where this is 50%, this is 50%. Let's just kind of estimate. Well, if that's true, then that means that if it's skewed to the left, the mean has to be to the left of the median, right? So then that mean has to be, maybe C or whatever, or somewhere here, whatever. Let's just assume that it's C. Well, then if the C is the mean, because it's to the left of the median, well, then it can't be E, right? So it can't be A. The area between B and F is 0.5. Between B and F is 0.5. Okay, so if I do this area, let's see. Does that make sense? Well, that doesn't make sense because that only leaves a little bit of area here and a little bit of area there. There's no way the black, if this is the black part is 50%, then the red part must also be 50%, right? And that doesn't make any sense because they're not the same. All right, so it cannot be B. The median of the distribution is C. So like I said, the C is not quite the median. That's why I didn't use that as the median, because this area right here is not equivalent to this area right here. Okay, they're just not. That's why I put my median somewhere around here, you know, some kind of in between where the left side is equal to the right side in area. So it's definitely not C. The third quartile of the distribution is D. So the third quartile, if you recall, is where 75% of the curve is to the left, right, of the third quartile. So let's say they're saying that if this is D and that's the third quartile, then 75% of the data is covered here. Does that make sense? Well, if that's true, then that means that this portion right here is 25% of the black portion, right? Which means that the black portion is 3 times bigger than the red portion. So is that true? Well, like if I look at this, that might cover, so like this part right here might cover up to this, right? So that will probably, so let me just put this part in green. So this part right here is part of this, and then you have a little chunk of red here. So maybe like here, we're just kind of guesstimating. So that's already just one red in that black. Now if I do another red in that black, it doesn't seem like 3 of these reds will fit in one of the black. So it doesn't seem like the black is 3 times bigger than the red, okay? So that doesn't make any sense, right? Again, we're guesstimating here, but you can still kind of tell, right? And to eliminate any possible responses. So definitely not. The area under the curve between A and G is 1. Yes. A and G has to be 1 because it's a probability, it's a density curve, okay? So I wanted to explain the other ones to kind of show you why they're not true, and E is definitely true. All right, so 2.7. If the heights of a population of men are approximately normally distributed and the middle 99% have heights between 5 foot and 7 foot, what is the standard deviation of the heights in this population? All right. So first off, if you look at the answers are in inches. So this is tricky, right? They have the standard deviation in inches, but they have the heights here in feet and inches, right? So 5 foot 0 inches, 7 foot 0 inches. So let's convert these to inches first, right? Yeah. So let's do that. So 5 foot 0, that's 5 times 12 inches in a foot, that's 60 inches. And then 7 foot 0, so 7 times 12, it's going to be 84 inches, okay? So we got 60 inches to 84 inches. And it says the middle 99.7%. So that means, remember, the empirical rule is 68, 95, 99.7. So that means in a normal distribution, we would expect that 1 standard deviation away, we would have 68% of the curve. 2 standard deviations away, we would have 95% of the curve, and then 3 standard deviations away, we would have 99% of the curve. So that means we're here from there to there is 99.7%. Okay, and we know that that distance from there to there is 5, so this is 60 inches, and this is 84 inches. So that's a distance of 24 inches, right? Okay, so then, and we know that it's 3 standard deviations out. So, so that means we have 1, 2, 3, 4, 5, 6 spaces there. So we got 24 divided by 6, which is 4 inches. So each of those spaces has to be 4 inches, right? So that you can have 3 standard deviations to the right, 3 standard deviations to the left of the middle. So the answer is C. All right, so 2.8, the distribution of the time it takes for different people to solve a certain crossword puzzle is strongly skewed to the right, with a mean of 30 minutes and a standard deviation of 15 minutes. The distribution of z-scores for those times is, all right, so they got some options here. Okay, so now remember that to calculate the z-score, you would do the x minus the mean divided by the standard deviation, right? So if I wanted to get the mean of this distribution, right? So if I wanted to get the new mean, so let me see, this is the new mean, and this is the old, right? So that means I need to take the so if I take this right here and I transform it, well, what's going to happen to the mean? Well, the mean is going to behave the same way. If I take each of the data points and I subtract the mean, right, then that's going to affect the new mean in the same way, right? I should really call this new. So it's going to also affect the average by subtracting by that same amount. Okay, so if I subtract 5 from each of the data points, then I would expect that the average would be 5 less, right? So same thing here. We're going to subtract. It would be we're going to subtract by the new. Sorry, we're going to subtract the old mean, right? We're going to subtract the old mean minus. We're going to do the old mean minus the old mean, right? Because we're taking the mean, the original mean, and it's being impacted by taking away the old mean, right? I know it sounds weird, but for example, if the average of a set of data was 5, right? And I obtained that, let's say this is x1, x2, x3. Let's say I took away 2 from each of the numbers, right? And the mean was 5. Well, then I would take the old mean minus 2, and that would give me my new mean, right? Well, what if I took away 5 from each of those data points instead? Well, then the new mean is going to be the old mean of 5 minus the value of 5, which is 0. Well, that's exactly what we're doing here. We know that the mean is 30, right? And so we're just subtracting, and we subtracted 30 because that's what we're doing in the formula. So it's going to be 30 minus 30, okay? And then it says we're also dividing by the standard deviation, all right? So the new mean is going to be the old minus the old, so it's going to be 30 minus 30 divided by the sigma. What was the sigma? It was 15, which is going to be 0. All right, so that's my new mean. Now, what's going to happen to my standard deviation? Well, my standard deviation is not going to be affected by subtraction or addition, but it is going to be affected by division, okay? So my new standard deviation is going to be my old standard deviation, right? But not minus the mu old, right? Because we're not, it doesn't affect, addition or subtraction does not affect it, but division does. So we're going to divide that by the old standard deviation. I should really call this old over here, by the way. Okay. So yeah, so the new standard deviation is going to be the old standard deviation divided by the old standard deviation. Well, which is going to be 1, right? So the new standard deviation is 1, the new mean is 0. Now, what do transformations do to the shape? Well, the original shape is strongly skewed to the right. Addition or subtraction, multiplication or division do not affect the shape. So whatever the original shape is going to remain intact. So the new shape is still going to be skewed to the right. So therefore, the answer is it's not going to be normally distributed. It is going to be skewed to the right, but the mean is not going to be that because it's going to be transformed. It's going to be skewed to the right with a mean of 0 and a standard deviation of 1. Okay? You just have to understand transformations at the end of the day. The shape remains intact. However, the mean gets affected by addition, subtraction, and division, multiplication. The spread does not get affected by addition, subtraction, but it does by multiplication and division. All right, number 9. So for the EPA requires that the exhaust level of each model of motor vehicle can be tested for the level of several pollutants. The level of oxides of nitrogen in the exhaust of one light truck model was found to vary among individual trucks according to an approximately normal distribution, with a mean of 1.45 grams per mile driven, standard deviation of 0.40 grams per mile. Which of the following best estimates the proportion of light trucks of this model with the NOx levels greater than, so it says greater than 2 grams per mile. Okay, so it's a normal distribution. So we're going to show you how to do this with a calculator, but also with the just by basic modeling, right? With the basic distribution using the z-score and all that stuff. So we know that the mean is 1.45. The standard deviation is 0.40, so we add 0.40 to this, we get 1.85, keep adding 0.40, 2.25, and then 2.65. And you can do it on the left side, but there's no point because they want it to be greater than 2, so they want it to be 2 or more, right? So there we go, we got 2 or greater, so we're going to shade to the right. So that means that we're gonna convert this to a z-score. So we're gonna convert this to the 2 to a z-score. Okay, so we got z is equal to x, which is 2, minus mu 1.45 divided by a standard deviation of 0.4. So we do the math here. We got 2 minus 1.45 divided by 0.4. So that's 1.375. So it's about 1.4 or 1.38. Sorry, we got to round it to 2 decimals. It's about 1.38. So let's look up the z-score on the z-table. So we're going to look at table A. Okay, so here we go. We got a z-score of 1.38. So we're going to trace down where they intersect. So they intersect here, 0.9162. That's going to be my area. That's going to be my area to the left, okay? Not to the right. So it's going to be 0.9162 is my area there. All right, 0.9162. Let's go back to my picture. So this is this area right here, 0.9162. So to get the area on the right, I got to do 1 minus 0.9162, which is 0.0838. So about 8.38%, something like that, have to be there. So it looks like it's got to be B. That's the closest one to that, 8.46%. So let's show you how to do this with technology, okay? So to do this with technology, you're going to be using the normal CDF function, okay? So let me show you how to do that here. All right, so we're going to hit second var, and we're going to hit the normal CDF function, so number 2. Now, we want the area to the right, so our lower bound here is going to be 2, and our upper bound here is going to be infinity, right? Or we can't do infinity on the calculator, so let's do like 1,000, all right? A big number, okay? So let's change this lower to 2, and then the upper to 1,000. That's fine, or 1,000, or 10,000, whatever. And then the mu is 1.45, and the standard deviation is 0.4. Okay, and then figure out what our area is. So if you so if you have a calculator that doesn't have that, you just use this, right? Normal CDF 2. Let me see if I can show you that function. We got 2, and then comma, and then the 10,000 number, comma, the 1.45, and then the 0.4. All right, so we get an area of 0.0846. That's exactly what they got on the in the multiple choice. So the answer is B. So using the calculator is way faster than doing this. This would be good if you had a free response. If you're just doing this on the AP exam and they ask you this type of question, definitely use the calculator. It's going to save you a whole bunch of time. All right, so number 10. Until the scale was changed in 1995, SAT scores were based on a scale set many years ago. For math scores, the mean on the old scale in the early 1990s was 470, and the standard deviation was 110. In 2016, the mean was 510, and the standard deviation was 103. Gina took the SAT in 1994 and scored 500. Her cousin Colleen took the SAT in 2016 and scored 530. Who did better on the exam, and how can you tell? All right, this is a good question. So who did better? If you just looked at the absolute numbers, you would say, okay, well, I mean, Colleen had a higher score. However, remember that on the SAT, this was many years later, right? This was 22 years later. So a lot of things changed. So it's possible that Colleen actually did worse. So let's figure it out. Maybe they did the same as well. Who knows? Let's calculate it. So we're going to calculate the z-scores, and compare them. So we're going to do the z-score for Gina and compare that to the z-score for Colleen. All right. So Gina, she took her test in 94. Good old days there. And so in the early times, her score, she said, was a 500. The average was 470 back then, divided by the standard deviation back then was 110. Now, Colleen scored a 530. However, the average has increased since then. And so in 2016, the new average is now 510, and the standard deviation is 103. Okay, so let's see who did better. So if I calculate the first part, it's going to be 30 divided by 110. That's going to be Gina's. So about 0.27. And then we have, let's do Colleen's. That's 20 divided by 103. It's 0.19. All right, so if I were to graph Gina's on the standard normal distribution, she's going to be, this is 0, this is 1. Gina will be here at 0.27. That's an approximation. That's not really, this is an exaggeration because it's actually not going to be there. So let me kind of draw it out. I'm going to stretch out the normal distribution. Let's say that's 0 and this is 1, let's just say. So Gina might be here, but Colleen is going to be over here, 0.19. So you can see that Gina actually scored higher than Colleen. So Gina is at a higher percentile. So interestingly enough, she scored less absolutely, but relatively, she actually scored higher. So her standardized score is higher. So so the answer is C. All right, so let's look at the free response. The dot plot gives the sale prices for 40 houses in Ames, Iowa, sold during a recent month. It says the mean sale price was $203,388 with a standard deviation of $87,609. Find the percentile of the house indicated in red on the dot plot. All right, so we got the house in red. So we got this dot here. And so we need to count how many dots scored below. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So we got 26 houses. And then we're going to count the red dots. So that's going to be 27. Okay. So 27 where we're at the red dot or below it, right? We're less than or equal to the red dot. So that's a total of 27 from here to that red dot, including that red dot. So that means the percentile is going to be 27 out of, and then says there's 40 homes times 100. So that's going to be approximately 68th percentile. All right. It says calculate and interpret the standardized score or the z-score for the house indicated by the red dot, which sold for $234,000. So that's my x value. So we're gonna calculate the z-score. So the z-score is the x value minus the mean. Now they said that the mean sale price was $203,000, $203,388, with a standard deviation of 87,609. All right. So here we go. We do that. We get about 0.35. All right. So what this means, if we want to interpret it, this means that the sale price for the house is above average, right? It's 0.35 standard deviations above the average price. So the sale price for the home is 0.35 standard deviations above or greater the average sale price for the homes in the sample. Okay, so that's the interpretation. All right, so that takes care of number 11. Number 12, a study of 12,000 able-bodied male students in the University of Illinois found that their times for the mile run were approximately normally distributed, with a mean of 7.11 minutes and a standard deviation of 0.74 minutes. About how many students ran the mile in less than 6 minutes? Okay, so it says less than 6 minutes. So we know that we're doing a normal distribution, and we got 6 here, and we want the area to the left, right? So we want to figure out what that percentage is on the left side of the curve. So we need to convert the 6 into a z-score. All right, so 6 is the x value. So let's convert that to a z-score. We got x minus mean is 7.11, divided by standard deviation, which is 0.74. So you do that. Let's see what we get. Yeah, let's actually draw the normal distribution just so that we show our work, because this is a free response question, so we do want to show our work here. So we're gonna draw the normal distribution. Sorry, I did the best I can. You draw the best you can. So here, this is 7.11 minutes. This is the mile run time. Okay, and then we're gonna add 0.74 to that. So that's 7.85. We're gonna do that 2 more times. Okay, do this, 6.37, subtract 5.63, and right here is 4.89. And so we want this to be 6, so we're shading the area to the left. All right, so that's our work. And we're calculating the z-score now, so when we calculate the z-score, it's going to be negative 1.5. All right, so now that we got the z-score, we're going to use table A, and we're going to look up the area. We're going to look up negative 1.5, okay? So we got negative 1.5, negative 1.5, 0, all right? So that's got to be 0.0668. All right, so there's our area and this is our area to the left. So 0.0668 is that red area in my graph, 0.0668. So let's use that. Okay, so when I show my work, we're going to say, okay, well, that means that the probability that my x value is less than, what was the number? It was less than 6 minutes, right? Is equal to 0.0668. Now they don't want the percentage, they want the how many students, right? So we know that there's 12,000 able-bodied students. So we're going to take that percentage and multiply that by 12,000. Okay, so 12,000 students times 0.0668. All right, and that will give us our, so we get about 801.6 for that if we multiply that, which is approximately 802 students. All right, so there's your answer. So about 802 students ran less than 6 minutes, ran the mile in less than 6 minutes. All right, so that takes care of part A. Let's show you how to do that on the calculator as well, just, if you want to use technology. So let's go ahead and show you here. So again, we're going to hit second vars. We're going to go to normal CDF. Remember, we wanted the area on the left side. So the lower bound's going to be like -1,000 or -10,000, whatever you want it to be. As long as it's a big number, but big, but no negative number. Then go down to the upper. Now the upper, remember, has to be the 6 that we provided, right? So our upper is 6. And then for this, the mean was 7.11. So let's do that. The standard deviation, I don't remember what the standard deviation was. It was 0.74. All right, enter. So there you go, 0.0668. So that's pretty much what we got. All right, and then we can multiply that by the 1,200 students. Was it 1,200? Trying to remember how many students it was. Yeah, 12,000. So sorry, let me go back here. 12,000 students. So yeah, about 802 students. That's pretty close to what we got. All right, so it takes care of that. Part B. So when you do that calculator, you have to provide your work for that, right? So if you're just using the calculator, you have to say, okay, well, normal CDF, then, your -1,000, right, for your lower, your 6 for your upper, 7.11, and then your standard deviation of 0.74, okay? So you have to provide that and say that that's equal to 0.0668. And then, of course, you multiply that result by that 12,000 to get the answer, okay? So if you're using a calculator, you need to show supporting work for that. You need to actually explain that. Okay, so next one, it says approximately how long did it take the slowest 10% of students to run the mile? So the slowest 10% means the greatest 10% of times, right? Because slow means your time is larger. So you got to be careful here, okay? A small time means you're fast, right? In this case, to run a mile. A large time, you're slow. So they're actually talking about the bigger times. So when we show our work, right, we're going to basically say, okay, so let's show our work here. This is for part B. We have a normal distribution with our times, same ones that we had before, ... I'm not going to write all of them down, but normally you would show that, right? Then you have, okay, well, we need to figure out how many students ran the mile in less than how long was the slowest 10%? So that means that we need to figure out, okay, well, what is this time? X is equal to question mark, okay? So what is that time such that this area is 10%, 0.1000, okay? So that's what we're looking for, all right? So that means the area to the left of that is 0.9000, right? Because 1 minus. These two probabilities must add up to 1. And so I'm going to look this area, I'm going to look up 0.900 up in the table because, again, the table gives me the area to the left, right? So we need to look up 0.9000. As close to that as possible, as humanly possible, according to the table. All right. All right, so let's go down here. So 0.900. This looks like to be the closest possible value to that. Then the z-score is 1.2, 1.28. Seems to be my z-score, 1.28. All right, so we got 1.28 for our z-score. Okay, so that means that the z-score formula is x minus mu divided by sigma, right? So we got z is 1.28. We don't know where our x value is, minus our mean is 7.11, and our sigma was 0.74. So here we go, we're trying to solve. So we're going to multiply both sides by 0.74 to cancel. And then we're going to add 7.11 to both sides to cancel that out. So we end up getting x is equal to 7.11 plus 0.74 times 1.28. So we just got to do the math there. So the math there gives us about 8.06 minutes. Okay, so that means this time has to be 8.06 minutes. All right, so hopefully that made sense. So we're going to show you how to do this on a calculator. The calculator will make quick work of this type of problem. The calculator is actually very beneficial because you don't have to do all these calculations. However, it's very good to practice doing this because you show your work and you maximize your points when you're showing your work like this. And then you get your answer. Now, for this, you're going to need to use the inverse function. The inverse function is when you don't know what the x value is or the z-score is, right? And you're trying to figure out what it is. The other function, the CDF function, it is used when you're trying to figure out what the area is. Here, they already told you that the area was 10%, right? So we didn't have to do that. Now, we have to provide 90% as our area when we use the inverse function, okay? So we're going to hit, so let's bring this up. So we have second vars. We're going to do the inverse normal function, so number 3. Then we have to provide this area. We have to provide the area to the left or it's not going to be correct, all right? You don't have to put the 3 zeros there. You could just put 0.9. Now the mean is 7.11. Standard deviation is 0.74. Sorry about that. Let me delete that. 0.74. All right, and then there you go, 8.06. Very quick. It took care of all this stuff really quick for you. Again, to show our work for that, we have to say, okay, well, we're doing inverse norm. The area is 0.90 or 0.9. The mean is 7.11, and the standard deviation is 0.74. And that provided us with the 8.06 minutes. Okay? All right, so I showed you a couple of different ways to do it, which means that this video is going to be longer, but at least I'm showing you all the different ways. All right, so here we go. Last problem. So a study recorded the amount of oil recovered from the 64 wells in an oil field in thousands of barrels. Here are, I'm sorry, I skipped part C, so let me go to that. So I didn't want to skip a part. Suppose that these mile run times are converted from minutes to seconds. Estimate the percent of students who ran the mile in between 400 and 500 seconds. Okay, so these mile times are converted from minutes to seconds, and then you're doing the miles in between from 400 to 500 seconds. All right, so this is actually a transformation question, right? Tied in with a normal distribution question. So this is a good one. So remember, to convert from minutes to seconds, I got to multiply by 60, right? So that means that if I'm doing a transformation, I'm taking each of the times and I'm multiplying it by 60. So what is that going to do to the average? Well, that's going to multiply the average by 60 as well. The spread, the standard deviation, will also be multiplied by 60 because the spread is affected by multiplication and division, but it's not affected by addition and subtraction. So again, remember that. So here we go. So we need to show our normal distribution with the new times. Okay, so let's do our normal distribution. So now we got 7.11 times 60. So our new mean is going to be 7.11 times 60, which is 426.6 seconds. And then we got our standard deviation. It was 0.74 times by 60. All right, and that's going to be, do it on the calculator, 44.4. All right, 44.4 seconds. So we're going to be going by that amount. So we got 426, and yes, this is a free response. So we're showing all of our work. So yes, we would have to show our work here to get, to maximize your points, right? So we got 515.4. If I add, I'm going to add another 44.4 to that, 559.8. All right, continue here. Subtract, so that's 382.2, 337.8, and then lastly 293.4. So there's our normal distribution for the times, and we want it to be from 400 seconds now to 500 seconds. That's what they were asking for. We want to shade the area in between here. Okay, so there we go. So let's calculate our z-score. So we got two z-scores that we got to do. So z1 and z2. We're going to do z1. This is x1. This is x2. All right, so z1, 400 minus the mean is 426.6 divided by the standard deviation, 44.4. So we get about negative 0.60. Now z2 is going to be 500 minus 426.6 divided by 44.4. Yeah, 1.65. All right, so those are my two z-scores, and so what we need to do is we need to subtract those areas, okay? So the probability that the x value is between 400 and 500 seconds is equal to the probability that x is less than 500 minus the probability that x is less than 400. We got to subtract the two times. We got to subtract for when x is 500 or less than, and then when x is less than 400. Basically looking up these two z-scores. So look up both z-scores and then subtract them. That gives us the area in between. Okay, so when x is less than 500, that means that we're looking for a z-score of 1.65, right? So let me just translate to this two z-scores. So this translates to z-score being less than 1.65, minus, that's a less than symbol there, sorry, minus the probability that a z-score is less than negative 0.60. Okay, so that's how that translates to z-scores. So let's look up the z-score, 1.65. So that's 1.65. So it's 0.9505, 0.9505. Okay, so go back here. We got z is less than negative 0.60. So we got to go to the negative side. Negative 0.60, 60. So that's 0.2743, 2743. Alrighty, so we're going to subtract those two things. So we get 0.6762. Okay, so that it says estimate the percent of students. Okay, so this is in percent. So we're going to do this 67.62%. All right, so so about 67.62% of students who ran the mile had times between 400 and 500 seconds. Okay, you do want to practice writing the answers in context, okay? You know, because if you don't include context, they're generally going to mark you point, they're generally going to remove a point for that, so, or not give you the point, okay? Context is a big thing on the AP exam. You might get like a point for the answer, but then you won't get a point, the full point for the context, right? So you just want to be careful, and you want to include context as much as you can, as much as possible. And I didn't do that justice in this video, but I'm trying to remind you to do that. All right, so let's go ahead and show you, well, we kind of showed you with the calculator already, but we'll show you again with the calculator. We'll show you one more time. So if I wanted to do this with a calculator, here's what I'll do. So I need to do the cumulative density function, the CDF. So second vars, so normal CDF. I want to go from 400 to 500. And then my average was 426.6. And my standard deviation was 44.4. All right, so it's 0.6762. That's exactly what we got, 67.62%. Perfect. So that's another way to do it, just to check your work. So there you go. All right, so now let's look at solely number 13. Just that question. All right, so study recorded the amount of oil recovered from the 64 wells in an oil field in thousands of barrels. Here are descriptive statistics for that set of data from statistical software. All right, so they did the number summary for variable. The variable here is oil production, okay? So we're just looking at oil production. That's our variable. 64 for our sample size, 64 wells, and so on and so forth. Based on the summary statistics, is the distribution of amount of oil recovered from the wells in this field approximately normal? Justify your answer. This is a good type of question. Is it normal? Well, how do we justify whether it's normal or not? Okay, well, there's a couple ways to do it. So a couple things that you want to keep in mind. Well, first off, remember that if something is normally distributed, the mean and the median are at approximately the same spot, right? So the mean and the median are about the same. They're in the center. Here, if we look at this, the median is 37.80, the mean is 48.25. So the mean is greater than the median, so that indicates that the distribution is skewed to the right. All right. So if the mean were less than, it would indicate that it's skewed to the left. If it was equal, it'll indicate that it's approximately symmetric. Okay, so remember, if the curve is symmetric, the mean and the median are going to be the same. But that doesn't mean that if it's symmetric, it's normal, right? Because there's different types of distributions that are symmetric, right? You could have something like this. In that case, the mean is still equal to the median, right? So it's not enough to say that, oh, it's because of that it's symmetric, right? So that's something to keep in mind. So yeah, symmetric distributions in general have this property. We want to look at something else as well. We want to say, okay, well, if it's skewed, right, then it can't be normal, right? If it's significantly skewed, then it can't be normal. Well, that's what we're saying. Okay, so we're saying that if it's not equal, if the mean is not equal to the median, then it has to be skewed, right? Another thing to look for is look at the distance from the minimum to the median, okay? So remember that the distance from the minimum to the median has to be the same as the distance from the maximum to the median, right? That indicates that there's symmetric nature to the curve, right? And that indicates that there's no skew, right? If it's symmetric. But if I subtract that, so if I do 30, so let's just show our work off to the side. So we got 37.80 minus 2, that's 35.80, right? So that means that the area, the portion to the left side is 35.80 from the median. And then if I do the right side, well, the maximum is 204, so it's 204.90 minus 37.80. That's really big. That's 167.10. All right. Look how much of a difference. That means there's so much tail on the right direction and so little tail in the other direction. So if the median is here, the distance here is 160, is in the hundreds, right? 167. But the distance from here to here is only 35. So that indicates that there's some skew, and it's skewed to the right, right? So we're going to explain this when we justify our answer. So the data does not appear to follow a normal distribution. The mean is significantly larger than the median. In this example, the mean is significantly larger than the median. And then we'll say, okay, 48.25 is greater than 37.80. Just kind of showing the two numbers here. Also, the distance from the minimum to the median is 35.80. And the distance from the median to the max is 167.10. Of course, we have work here to kind of support it, so we could put that in our response, or we can leave it off to the side so that the graders can see it, right? But otherwise you can put it in your response. To the max is 167.10. These distances should be approximately equal. And the mean and median are roughly the same. in a normal distribution. Because the mean is greater than the median, and the distance to the right of the median is greater than the distance to the left of the median, this indicates the distribution. This indicates that the distribution of oil recovered, again, I'm introducing the context. What is the distribution for? The distribution is oil recovered, right? Is skewed to the right. Okay, I know it's a lot of explanation, but again, you know, the more you can get yourself to kind of explain each process and show supporting work, the better, right? As long as you don't get to the point where you write a detail in your response that contradicts, right? You definitely don't want to do something that contradicts, because if you have contradictory evidence or a contradictory explanation, then what they're going to do is they're going to take they're basically going to give you the lesser amount of points, right, possible. They're going to do, it's going to be in such a way that when they grade it, they'll look at the wrong response and use that in their grading, right, the incorrect response. So you end up losing points. So you definitely don't want to contradict yourself when you're explaining things. You want to be very clear. All right, that is the end of the video, guys. I hope you found this useful and informative. As usual, I'll see you in the next one.